All right. So, good evening and welcome to the third live session on the applied linear algebra for signal processing, data analytics, and machine learning. So, we will be covering some sample problems based on the contents that were covered in the week 3 of the course. And if you go back to your lectures, um, week 3 started with the notion of the Gram-Schmidt orthogonalization procedure that allows you to find a set of orthonormal bases for a subspace. And then we looked at the concept of Gaussian random variables or Gaussian random vectors. And we also looked at the special case of IID random variables. IID stands for independent and identically distributed random variables. So and then we moved on to the discussion on eigenvalues and eigenvectors of a matrix, and also briefly touched on the eigenvalue decomposition, or EVD for short. Finally, we also looked at the unitary and rotation matrices, which arise in a lot of applications, right? So, keeping these concepts in mind, let's get started with today's session. And for those who are attending their first session today, a quick introduction about myself. So, my name is Avik Mukhopadhyay, and I am a PhD research scholar at the Department of Electrical Engineering at IIT Madras. So, I'll be one of the TAs for this course. And every week we'll be having this tutorial sessions. Okay, so yeah, let's get started. And the timings are, as you know, Fridays 6 to 8 p.m. Okay, so good. So let's get started. Okay, okay. So let's start with the first question. I'll move to the other tab. Yeah. So please read the question. So you're given two vectors, x1 and x2. Therefore, corresponding vectors. So, and you're asked to come up with a set of orthonormal basis vectors for this same subspace using the Gram-Schmidt procedure, GSOP, Gram-Schmidt orthogonalization procedure. Okay, so this has been discussed in the lectures. We know the process, right? So in this case, it's very simple. Actually, there are only two vectors. I think someone wants to join. Okay, so as I was saying, like we have only two vectors in this case, and we know the process, right? So basically, we have to come up with an orthonormal basis. So they have to be basis vectors, and like they have to be orthonormal. Orthonormal means both orthogonal as well as unit norm. Okay, so and they should form a basis for the same subspace. Basis means basically like any vector in that particular subset can be represented or expressed as a linear combination of the basis vectors. And like it basis in general has two basic properties. They should be linearly independent set, as well as they should be a spanning set, meaning that their linear combination should span the entire vector space. So that is, any vector can be represented using a linear combination, appropriate linear combination of the basis vectors, and it need not be unique. Okay, I think someone's mic is on. So can you please mute yourself? I hear a background noise. Yeah, thank you. And in case of any questions or any queries, feel free to unmute and ask me, okay? Okay. So what is the step that we follow for GSOP? Basically, we take the first vector, which is x1 in our case, and we simply normalize it. Okay, we divide it by its norm, and we get a unit norm vector, which is our first vector of the orthonormal basis set that we want. And to get the next one, what we do is we take x2, the second given vector, and from x2 we subtract the component or the projection of the previous basis vector that we got along x2. Okay, so this projection along that x2, if we remove, it ensures that okay, it has no component along x2. So clearly the new vector that we will get in the next step would be orthogonal to the previously obtained orthonormal vector, right? So and we perform it iteratively. In this case, there are only two vectors, and of course, after doing that, we again normalize that vector to ensure that it is having unit norm. So finally, we will arrive at some two different vectors which are orthonormal to each other. Let's say v1, v2. Okay. So let's solve it. Okay. Okay. So what we are given is these two vectors, x1 bar, which is the vector containing all ones, and x2 bar, which is the vector containing these entries. Okay, so we are looking at the Gram-Schmidt procedure. Okay, so as I said, the first vector is simple, you know, let me call it v1. To get v1, you basically need to normalize the first vector, which is x1. So basically you divide it by its norm, correct? And what is the norm of x1? Can someone tell me quickly? 2, right? Yeah, it's 2. Thank you. So basically you perform this thing, right? You take the square root and take the compute the sum of the square of the sum of the elements. In this case, we have a real vector, so we need not take the magnitude square. In case of complex vector, we will have to follow that, but it's simply, you know, the L2 norm like this. Okay, and as he said correctly, so it is 2. Okay, and you get this. So this will be your first vector in the orthonormal set. And to compute the second one, as I said, you first have to do something. You have to subtract. Remember, you have to subtract that component, that projection. So I'll use a different notation. In fact, this same notation was used in the lectures also by professor. So basically, let me call it v2 tilde. So you take the second given vector, which is x2 bar, right? And from x2 bar, you subtract the component of x2 bar along the previously obtained vector, which is v1. Okay, this. So clearly it's an inner product, right? So it's like the overlap of those two vectors, or the projection. Okay, and along the direction of v1. So this is indicating that this is the projection component and this is along v1. Along v1, this is the projection of x2 along v1. Okay, so you're removing that part. So if you remove the projection along v1, so it is ensuring that v2 and the next vector v2 tilde that you are going to get would be orthogonal to v1, right? So yeah, and once you do that, you normalize v2 tilde. So you divide it by its norm to get the second vector in the orthonormal set. So let's find it first. So what is x2 bar? What is x2 bar? Given in the question, it is 1, 2, 3, 4, right? Yes, x2 bar is 1, 2, 3, 4. And how do you find this projection? This inner product of x2 and v1, you basically take the pointwise product, right, and add them up. So we have seen this in the first 2 weeks extensively. We have used inner products. So basically x2 and v1, right? So if you take the pointwise product multiplication and add them up, what you get is 1 times half plus 2 times half plus 3 times half and plus 4 times half, right? And v1 is simply, which you already obtained in the first step, is half times this. Okay, everyone is with me so far? Any doubts? Okay, good. So what you get is 1, 2, 3, 4, yeah, minus, and this, from this uh, first bracket you can actually take half common. You can pull a factor of half outside and you already have another half here. So half times half will give you 1/4, and you can actually write this as in this form. Okay, so what you are going to get is, so this will be 5 by 2 times 1, 1, 1, 1, correct? So 10 by 4 is nothing but 5 by 2, and this is nothing but, you have to subtract them. So 1 minus 5 by 2, then you have 2 minus 5 by 2, 3 minus 5 by 2, and finally 4 minus 5 by 2. Okay, so which is minus 3 by 2, minus half, half, and 3 by 2. So this is, if you take the half factor outside, it is minus 3 minus 1, 1, 3. Okay, and the last step, so this is v2 tilde. This is not yet normalized. Its norm is not equal to 1. To make it unit norm, we now have to find its norm and divide the vector by its norm. Okay, so what is the norm of this vector? So we have a constant factor of half outside, right? So that can be simply taken outside. Basically, if you do the square root of half square, you get half itself. So this is half times the square root of this elements of the vector, which is, right, and this is half times square root 20, which is half times 2 root 5, is equal to square root 5. Okay, so therefore you now can write v2 bar as v2 tilde divided by the norm of v2 tilde, which is 1 by 2 root 5 minus 3 minus 1 1 3. Okay, so what were the vectors that we got? So the v1 was half times 1 1 1 1, and v2 is this one 1 by 2 root 5 and minus 3 minus 1 1 3. And if you check with the options, it is the last option, option D. Okay, it is matching with option D. So the correct answer is option D, which is this set. Okay, all right. Okay, then let's move to the next question if there are no doubts. Okay, so read the second question. So we are given IID 0 mean and variance sigma square Gaussian random variables x1 x2 all the way till xn, although in generally textbooks the uppercase alphabets are used to represent random variables, but in this case I am using small or lowercase. So yeah, so these are IID Gaussian random variables. So they are independent, independent and identically distributed random variables. Okay, all of them have zero mean and variance sigma square, and they follow the Gaussian distribution. So and we are given a real vector, n-dimensional real vector a bar with the elements as a1 a2 all the way till an. So I have written it in the form of a row vector, but it's actually transpose of it. So it's a column vector of a1 a2 all the way till an. It's an n cross 1 vector, and this x bar is your Gaussian random vector, which consists of these Gaussian random variables, right? x1 x2 all the way till xn. So you have to find the variance of the quantity a transpose x bar. Okay, and in fact I think we have seen this a very similar kind of thing in the lectures as well. So yeah, so this is the question. Okay, so this is on the concept of Gaussian random variables. Okay, so let me note down a few things. So IID. Okay, IID stands for independent and identically distributed. So they are zero mean, it's given in the question, and variance sigma squared Gaussian random variables x1, x2, all the way till xn. So all these xi's, right, they are basically distributed as Gaussian with zero mean and variance sigma square. This is how you represent them. And your Gaussian random vector is this vector, okay, right? So we have to find the variance of A transpose X. But before that, let me just define what is given. Okay, basically your A is given as A1, A2 all the way till AN. Okay, this vector, and it belongs to the n-dimensional real vector space. So this A1, A2, they are real numbers. Okay, so what is the variance of A transpose X? Okay. Okay. So clearly you see the A transpose X. This is basically, I mean, is it a vector or a scalar? A transpose X. A bar transpose X bar. Yes? Anyone?
Scalar?
Yeah, it's a scalar basically. So it's clearly an inner product, you see. Um, so you take the transpose of A and X are individually vectors, but you take A transpose, so it becomes a row vector 1 cross n, and X bar is n cross 1. So their product is the inner product, which is a 1 cross 1 scalar basically, and it's like A1 x1 plus A2 x2 plus so on till AN xn, right? So this is a scalar. It's the linear combination of the Gaussian random variables where the weights are your A1, A2 and so on till AN. Okay. Okay. So good. So let me introduce some other notations. So xi is distributed as this. Xi's are your Gaussian random variables. So and all of them have zero mean, right? So let me denote like the expectation. Mean is nothing but the expectation, right? Expectation of all these xi's. Let me use the notation mu suffix, or let me come to that later maybe. E or expectation of xi is equal to 0, right? Okay, okay, good. So now and this is the x bar is the vector of those random variables, so that's the Gaussian random vector, and the expectation of x bar, if you have, I am denoting it by mu x bar, which is 0. It's actually the 0 vector actually. Okay, so this is the mean vector, it's a 0 vector. Okay, now we are asked to find the variance of A transpose X. So let me use another variable. Let y, it should not be y because I mean it should not be y bar. It's simply a scalar, right? As I said. So let me call it y. Let y equals to A transpose X. Okay. So, what is the expectation of y? It's simply the expectation of a bar transpose x bar, and this a bar transpose, this a thing is just a constant thing. It's all real entities, and the variable here, the random variable, is that it is captured in the x bar thing, right? So since a bar transpose is a constant vector, so you can pull it out of the expectation. So this goes outside times expectation of x bar. And what is expectation of x bar? We have seen it is 0, because all the expectations of these individual random variables are 0. So the expectation of x bar gives us the all 0 vector, right? So this is 0. So this is again 0. Okay. I mean, let me write it again. So this is a bar transpose times your 0 vector, right? So that will give you simply, basically it's a1 times 0 plus a2 times 0 and so on till an times 0. So this is the scalar 0. Okay. So wherever you see bold like this means vector. This means 0 vector. Okay. So this is 0 vector. Okay. This is scalar. And finally, this is also scalar. Okay. Okay. But we are asked to find the variance, right? So variance of y, you know from your high school mathematics that it has this form. It can be written as expectation of y minus the expectation of y, right? Mm, this thing whole square. Correct? This is the definition of variance. That's how we define. Okay. And so what are we getting here? The expectation of y minus, what is the expectation of y? We just found it's 0. So this is 0, right? So this is expectation of simply y squared, right? And what was our y? It was that inner product, right? A transpose x. Okay. So this is A transpose x, the whole square. And remember that A transpose x is nothing but your, what is A transpose x? Okay, this is simply the inner product of the vectors A and x, which is nothing but a1 x1 plus a2 x2, so on till an xn, right? So you see, what is the, essentially what is the problem in our hand? We are given a set of, IID random variables, Gaussian random variables x1, x2 all the way till xn. And now what we are doing is we are doing a linear transformation of those variables. This whole thing a1 x1 plus a2 x2 so on till an xn, it's a linear transformation of your Gaussian variable, right? A linear combination rather. So, and you are asked to find the variance of this quantity. That's the essential problem in hand. So since this thing is a scalar, we are taking the square of a scalar. Um, I can write it like this times, okay. Okay, so basically I've written it, I mean, splitted the square as multiplying it 2 times. So, and now keeping the first term as it is, A transpose x, now I can also write A transpose x is also the same as x transpose A. Same only, right? You'll end up in the same thing. So I can also write it as X transpose A bar. Okay, since A transpose X same as X transpose A bar is the same scalar that you'll get. So this is nothing but mm, okay. So again, in this case, we have this A transpose and A terms, which are not your variables, random variables. So you can keep them out since they are constant entities. You can uh, keep them outside your expectation. So what you will get is, so this first term A bar transpose comes out, and you have expectation of X bar X transpose, right? This thing, and similarly this last A bar also, you can move out of the expectation. Now what is this thing? Do you recall what this thing from the lectures? Expectation of X transpose X, I mean expectation of X transpose, where X is this Gaussian random vector. Do you remember what this was? This is actually, and remember, we are dealing with IID random variables. If you go back to your lecture notes, this turns out to be sigma squared times your identity matrix, and this is called as the covariance matrix. Okay, for IID, for IID random variables, IID Gaussian random variables, I should say. Okay, so this we have seen in the lecture. So just recall lectures. Okay, so this is sigma squared times identity. So basically you get a diagonal matrix, right? All the off diagonal elements are 0, and along the principal diagonal you have sigma squared as the entries. Sigma squared is the variance of all the Gaussian random variables, right? So this is A transpose sigma squared I identity acting on vector A. So this is sigma squared. It's just a scalar quantity. It's a constant value, so you can bring it in front like this, and you have A transpose, an identity matrix acting on a vector A will give me the vector A back, right? So this is this thing. And what is A transpose A? What is this thing? How can I rewrite this? Remember, A is that vector of A1, A2, so on till An. So what does A transpose A denote? Yeah. So A transpose A is nothing but the inner product of A, the vector A with itself, which is nothing but the norm squared, right? So this is nothing but your norm squared, the norm of this thing squared, right? So A bar transpose A is nothing but, this this thing A1, A2 all the way till An. You're finding this inner product. So what are you going to get? So this is A1 squared plus A2 squared all the way till An squared, and that's the square of the norm, right? Square of the norm of A, right? So this is this thing, okay? This is your answer. Is it clear?
Yes.
Yeah. Okay, good. And in fact, if you want to do it in a different way, you can also do that. I mean, what this quantity essentially is, as you have seen, A transpose x bar is nothing but A1 x1, A2 x2, all the way till An xn, right? And we have seen that the so I was denoting this by, sorry, again I'm using y bar. It's simply a scalar y. So I was denoting it by y. Okay, let me join. Okay. Okay, so what is the other way to, approach this is, and we saw that the expectation of y was 0, right? We saw that because expectation of y is how much? We have y as A transpose x, so A transpose comes out of the expectation, and expectation of, we are left with expectation of x bar, which is the 0 vector. So clearly we get A transpose times the 0 vector, which is basically the scalar 0, right? It's the inner product of the A vector and the all 0 vector, which is again a 0 scalar. Okay, so the variance of y is how much? It's basically, as I said, you can write this as expectation of y minus the expectation of y, like this, right? And this is nothing but expectation of y squared, since expectation of y is 0. So this is what? This is y is this thing whole squared, correct? So if I squared this whole quantity here, what do I have inside expectation? So you take them like the take the squares of these elements individually. So first term squared will be a1 squared x1 squared. Okay. Second one would be a2 squared x2 squared. So on till an squared xn squared. And we also will have the cross terms like the pairwise products. Let's say 2a1. Let me just move this bracket for now. So let's say the product of 2 times the product of first and second term. So this is 2a1, a2, x1, x2, and so on. You will have other terms as well. So like this, okay? And now using linearity of expectation, you can write this as follows. So a1 square comes out of the expectation. Similarly, a2 square comes out of the expectation, right? And so this is an squared comes out of the expectation, right? And so this 2a1 a2 also comes out of the expectation, and you have expectation of x1 x2, and likewise other pairwise products. Okay, now what is this expectation of x1 squared? So remember the variance of x1. This is simply the variance of x1, right? Variance of x1 is nothing but x1 minus expectation of x1, this thing whole square. And since all these random variables have zero mean, so this is 0. Expectation of all xi's are 0. So this is expectation of x1 square simply, right? So this is the variance. And what is the variance? It's simply sigma squared given in our question. All have identical variance since they are IID. So this is sigma squared. Similarly, this is sigma squared. Similarly, this term is also sigma squared. Okay, so what do we have? A1 squared sigma squared plus A2 squared sigma squared plus so on till an squared sigma squared plus this term here 2a1 a2. Now this is a product of two IID Gaussian random variables x1 x2. and I have expectation outside. Can I write it like this? Expectation of xi, x1 times expectation of x2. Yeah, I can write this because they are IID and so they are independent random variables. If these two are independent, in general there could be n number of such terms. If I have n independent random variables, then expectation of if I have x1, x2 all the way till xn inside the parenthesis as product terms, then I can split them as expectation of x1 times expectation of x2 times all the way till expectation of xn using. So I arrived at from here to here by independence, okay, of random variables. Are all of you familiar with this? Like I can write it like this, split the product like this if they're independent random variables. I mean these are things which are taught in the probability course. Yeah, someone was trying to say something. I didn't get you. I think someone was just trying to say something. I didn't hear properly. Okay, so never mind. So this, what is expectation of x1 now? This is 0. Expectation of x2 also 0. Similarly, all these cross terms that you will have, they will be 0, right? You can split them up using the property of independence and all that will contribute to nothing. It will vanish basically, it will be 0. So ultimately what you have is sigma squared can be taken as common, a1 square, a2 square plus all the way till an squared, and this whole thing is simply the norm squared of the vector a, right? And we landed up in the same thing as before, okay? And if you check with the options, it is option C. So our answer is option C. Okay, so these are straightforward problems, and yeah. In the assignments also, I think the questions are pretty straightforward, nothing complicated. Okay, let's move to the next one. Okay, now this is again. So another motivation to study this Gaussian random variables, as Professor Jagannatha mentioned, is the lot of applications. Since they arise in lot of applications in the context of communication, signal processing, and in fact in machine learning, right? One of the classical problems in machine learning is the classification problem, right? So we want to classify, let's say, an image into two classes. Uh, in this problem, let's say I have two classes, right? C1 and C2, and these two classes are modeled as Gaussian random vectors. Okay, so Gaussian variables, Gaussian distribution arises in these kind of applications in classification problems. Okay, so the task in hand is like you have two classes which are modeled as Gaussian random vectors with some mean vector and covariance matrix, and if you are given a new vector, let's say a new image or whatever that could represent anything, and your task is to classify that new vector into one of these given classes, whether it belongs to C1 or C2, which is the right choice. So in these kind of classification problems, these Gaussian random variables play a role. So in this case also it's the same thing, right? So the distributions are given of the two classes, Gaussian classes, and you have to find, okay, what is the, you basically in this problem what you are asked is what is the decision rule, what is the classifier. So when will I choose C1? When will I choose that X, the new vector X, belongs to the class C1? What is the condition for that? Okay, all right. So what are the given classes here? So the first class, which is class 1, right? This is denoted by C1, and it has a distribution, normal distribution or a Gaussian distribution. Uh, okay, this is a basically a vector, multivariate Gaussian. So the mean vector is minus 1, 2, and the covariance matrix is half, 0, 0, 1 by 4. Okay, and remember your lecture notes. So the notation that was used in the lectures was, this was mu1, that's the mean vector of the first class, and this was your covariance matrix. So the sigma notation was used, right? Okay, so this is your mean vector, and this is your uh, covariance matrix. So you see that in this case also, like the diagonal elements are non-zero and the off diagonal elements are 0. So 0 off diagonal elements 0 means like uncorrelated things, I mean the expectation of xi xj for I not equals to j is 0. Okay, so and similarly you have the second class, class 2, which has not the same but similar uh, with this mean vector. So this is my mu2 bar, and the covariance matrix is the same. Okay, like this. And this is again the same. It's sigma only. Now, so these two are your Gaussian classes, right? Sorry for my bad handwriting. Let me know, okay, if you're unable to understand Gaussian classes. Okay, task is to classify a vector, new vector x bar. It's a 2 cross 1 vector like this. And in the question specifically, we are asked what is the condition to classify x bar into the class C1. When do I choose C1? And if you recall your lectures, we choose C1 if you remember that there was some product of few quantities, you know it was particularly, it was like this: choose this C1 if mu1 bar minus mu2 bar transpose sigma inverse x bar minus the midpoint of mu1 bar and mu2 bar, which is simply their mean, mu1 plus mu2 by 2, right? This entire term is greater than or equals to 0. This was the condition. It has been discussed in the lectures. Okay, right. Okay, so can someone tell me what is this inverse of this covariance matrix, I mean sigma inverse, this term, what is this going to be? Sigma is given, this half 0 0 1/4. What is sigma inverse? Without even computing, can you tell me? So you see sigma here is, it's a diagonal matrix, right? Only the diagonal elements are non-zero. You see this thing, uh, only the diagonal elements are non-zero. This, this, and the off-diagonal elements are zero. You see, so these are called diagonal matrices. And for diagonal matrices, the inverse is simply another diagonal matrices with the diagonal entries being the reciprocal of its previous one values. Okay, so meaning that sigma inverse, sorry, sigma inverse is simply, so initially it was half and 1/4 along the diagonal, so you take their reciprocal, so it becomes 2 4, and the off diagonal elements are still 0. Okay, so this is for diagonal matrix, for diagonal matrix. For diagonal matrix, you can simply, find the inverse at just one line. So, okay, all right. So, what is mu one bar minus mu two bar? Let's now compute. So, you are given mu one bar and mu two bar. So, you can subtract these two vectors. Um, so, what you are going to get is so mu one bar is minus 1 2 minus mu two bar is 2 1. This whole vector, take the transpose of that, and sigma inverse we just wrote is 2004, right? And what is x bar minus this thing? So x bar is your basically given new vector that you need to classify. So this minus the midpoint of mu1 and mu2, so that is nothing but half, and okay, and yeah, so this whole thing inside, this should be greater than 0. If this whole thing is greater than or equals to 0, choose C1, else you choose C2. Okay, if this is less than or equals to 0, choose C2. It means it belongs to the other class. We only have two classes, so there are only two possibilities. Okay, so if you compute this, try to evaluate all these terms. What you are going to get is the first, this term becomes minus 3 1, this whole transpose, and you have 2004, that's your sigma inverse, and here what you have is this x1 x2, and this term, this midpoint would be this thing. Okay, okay, so what do I have? um, this is taking the transpose, it becomes a row vector, and so what is this? So this is x1 minus half and x2 minus 3 by 2. Okay, and dimensionally it's also correct. This is 2 cross 2, this is 2 cross 1. So if I multiply these two together, I will get 2 cross 1 vector, and I have in front 1 cross 2. So 1 cross 2 multiplied with 2 cross 1 is will give me a 1 cross 1 scalar. So of course that's what I am comparing with on the right hand side. The right hand side threshold is 0, it's a scalar 0. So in the left hand side also I will get a scalar. So makes sense. So what do I have? This is um, 2 times x1 minus half, 4 times x2 minus 3 by 2 should be greater than or equals to 0. So it's simply the inner product now. So this is so what do you have here? Minus 6x1 plus 3 plus 4x2 minus 6 is greater than or equals to 0, or minus 6x1 plus 4x2 minus 3 is greater than or equals to 0, minus 6x1 plus 4x2 greater than or equals to 3. Finally, uh, 6x1 minus 4x2 is less than or equals to minus 3. Okay, this is my condition for choosing C1 class, and it matches with the first option. See, so your answer is option. Is this clear? Yes. Uh, so far so good.
Yes.
Okay. Now let's move to the fourth one. Find the eigenvalues and eigenvectors of the following matrix A. So, what are the eigenvalues? What do you mean by eigenvalues? Yeah, feel free to participate. It's nobody is going to evaluate based on your answer. It's perfectly fine. If you know, if you don't know, then also it's fine. Are you familiar with eigenvalues? The concept of eigenvalues? How do we find it? Okay. Okay, no. Okay, fine. No issues. No issues at all. Let's see. Let us see. Okay. Where was I? Okay. Okay. So, and I just request you to. I mean, I'll just request one thing. Like, just since you have to, if you have registered for the course and you have this weekly assignments that you need to submit, right, within some due date. So for that you actually need to maintain a minimum pace that you are, you know, following along the pace of the course. So otherwise it will be difficult for you and it will be a lot of burden on you. Uh, especially with respect to submitting the assignments and time and so on. So as the videos are getting uploaded in the course web page, every week the contents are released. Now I think uh, till week 3 it's available in the course web page. So, and in fact it's the same old rerun of the old course, only the lectures are available in YouTube, only the recorded lectures. So you can go through them. Just be sure that you are also on the same page, otherwise it will be difficult. Okay, so yeah. So basically in this question you are given a matrix which is 0, -2, -3, -1, 1, -1, 2, 2, 5. This is the matrix. So what is the order of this matrix? What is the size of this matrix?
3 by
3 by 3, right? I mean, I'm assuming everyone is familiar with this. Like in general, we say a matrix is of size m cross n if it has m rows and n columns. So the rows are the vertical lines and the columns are the, you know, sorry, the rows are the horizontal lines and the columns are the vertical lines, right? So in this case, it's a 3 by 3 matrix. Clearly, there are 3 rows and 3 columns. And since the number of columns and number of rows are equal in this case, so these kind of matrices are also known as square matrix, right? Square matrix. So in general, like it could be a rectangular matrix where the number of rows and number of columns are different. Okay, so so your task is to find the eigenvalues and eigenvectors of this matrix. So before finding eigenvalues, what you do is you form something called the characteristic polynomial. Okay, and how do you get the characteristic polynomial? You basically take the determinant of a minus lambda times identity. Okay, are people familiar with determinants? Determinant of a matrix? Sorry, I couldn't hear you.
Oh, yes.
uh, okay, yes, yes, yeah, I mean, and in fact I have discussed the determinants in like previous sessions also. You can visit them later. Okay, so you take the determinant of a minus lambda I. Okay, so clearly this will be a function of lambda. Lambda is your the variable. So you can denote this by f of lambda, some function of lambda. Okay, some function of lambda, f of lambda. So this f of lambda is your characteristic polynomial. Okay, and at most this polynomial will have degree 3 because a is 3 by 3, and determinant is defined only for square matrix. I think you should be aware of it. So in this case it's a square matrix 3 by 3, so determinant makes sense. And in general, if it's an n cross n matrix, if you take the determinant of a minus lambda I, that will give you a polynomial of degree at most n. Okay, okay, so this is called the characteristic polynomial. So what is identity? So the identity matrix, in this case a is 3 cross 3. So for it to make sense dimensionally, you have to take identity of the same size. So your identity matrix that you have to take is also must also be of size 3 cross 3. So which is 1 0 0 0 1 0 0 0 1. Okay. So what is this A minus lambda I? What would that matrix look like? Can someone tell me?
Lambda in diagonal.
I am finding A minus lambda I. So you tell me what will be the entries here. Okay, all the entries. Just tell me.
Lambda 0.
I'm not sure whether it's problem from my end, but your voice seems to be breaking, so I can't hear you. I know that you are responding, but I am unable to hear you. Okay, so see, if you subtract lambda I from the matrix A, so in identity matrix, you see all the off diagonal elements are zero, right? So all the off diagonal elements of the matrix A will remain unchanged because in identity you have 0. So all these elements minus 2, minus 3, minus 1 which are not along the principal diagonal, they will remain as it is, right? Only these elements along the diagonal which is 0, 1 and 5, they will be affected if you subtract lambda times identity from them. So this will become minus lambda, this will become 1 minus lambda, this will become 5 minus lambda. Does everyone agree with me? Okay. So now to find the determinant of this thing, I mean, you can expand it. You usually expand along some row or column. That's fine. But since you always want you to have some sparsity, meaning that you want to have some zeros inside the matrix, so that your computations, number of computations are fewer. Let's say if you are expanding along the first row, uh, of a 3 cross 3 determinant, then and let's say two of the three entries are 0, then it simplifies your task, right, in computing the determinants. So why not, let's try to make this process simpler by modifying this matrix, performing some operations on this matrix that reduces this and introduces some zeros that will help us to compute the determinant faster. And using property of determinant, property is that, okay, are you familiar with these things like mm, oh, sorry, so this is I want to use a different color. Okay. So this is the first row, this is your first row which is denoted by R1, and this is the second row which is, sorry, which is denoted by R2. I mean, R stands for row in this case. And similarly, let me use a different color, perhaps this one. This one is your R3, third row, first row, second row, third row. Okay, all right. So the property, one of the properties of determinant says that if you add a scalar multiple of another row to a particular row, the determinant of the matrix remains unchanged. Okay, so meaning that let's say the ith row you are adding some constant k times some scalar times the jth row to the ith row and storing the result back in the ith row. So what does that mean? This means that Ri maps to Ri plus k times Rj, meaning that you perform this operation, that is you add a scalar multiple of the jth row to the ith row and store the result in the ith row. Okay, so if you perform this operation, the determinant remains unchanged. Okay, so we want to make use of these property. So we want to simplify, we want to use, and these operations are known as row operations. I have discussed them in the previous sessions. Please go through them. So I will try to introduce some zeros here, and using this property, I can write this as, how can I write this? If I make use of this property, let's say R1 goes to R1 plus R2 plus R3, meaning that I am adding the three rows and storing the result in the first row. So what happens to the entries now in the determinant? So what does it become? So I'm only changing the first row, right? The second and the third rows remain the same. The second row and the third row, they will remain unchanged. What I am doing with the first row is I'm taking the sum of all the three rows and storing it. The result I'm storing in the first row. So can someone tell me the entries of the first row now? Yes?
Minus lambda minus 1 plus 2.
Yeah, exactly. So minus lambda minus 1 plus 2, which is nothing but 1 minus lambda. So this is 1 minus lambda. And similarly, what about the other entries?
1 minus lambda.
1 minus lambda,
1 minus lambda.
1 minus lambda. So you see the pattern. So all the elements along the first row are now 1 minus lambda, are now 1 minus lambda. Okay. And again, another property of determinant is that I can simply take this common factor from a row. Okay. If you know some of if you are able to get a scalar factor common from a particular row, you can simply pull it out of the determinant. So I am taking 1 minus lambda common from the first row. So the first row will now become 1 1 1. Okay. All right. So and now on this determinant again, let's say, remember my task was to get some zeros. So now if I do this another row operation, R1 maps to R1 plus R2. Then what do I get? I have this constant factor outside, which is okay, fine. Now what do I have? The second and third row remains unchanged. What about the first row now? If I add the first and second row and store it in the first row?
0.
0. This is 2 minus lambda. And again, I get another 0. So you see, you have simplified. You obtain two zeros. Okay. Maybe you could have done some other sequence of row operations, but it's fine. I have been able to introduce some sparsity, some zeros. And now, if you expand, now you can expand the determinant, right? Expand, expanding along. What's the best way to expand? You can expand along the first row because the first row has two zeros. Along R1, the first row. What do you have? This already this constant factor is sitting outside. So 0 times whatever is 0, and for this element 2 minus lambda there will be a factor of minus 1 because it is the 1 comma 2th entry. So minus 1 to the power 1 plus 2 is negative. So I think you should know how to find the determinant. I'm not going through that. And basically what you do is you take its minor. So you remove this particular row and this particular column. So you are left with minus 1 to 5 minus lambda. That submatrix determinant you have to take. Okay. So that will basically give you that will basically give you this. So this is I hope you know how to find the determinant of 2 cross 2 matrix. Basically you multiply the diagonal elements and also you multiply the off diagonal elements and subtract the product of off diagonal elements from the product of the diagonal elements. Okay, so what you will get is this. So we have been able to, so this was our f of lambda, right? We started with this, the determinant of a minus lambda I. So this is our characteristic polynomial. You can also, I have factorized it in a nice fashion here. The reason will be clear in a minute, but you can express it in a cubic polynomial, right? So it's a third degree polynomial. It's a cubic polynomial. So you can expand that also. It's fine. But the reason why I have factorized it is to find the roots of this polynomial. And why do you need the roots of the polynomial? Because the roots of this polynomial, that is the roots of this characteristic polynomial, are the eigenvalues of the matrix. Okay, that's what was asked in the question. So what are the roots of f of lambda here? Yeah,
1, 2, and 3.
1, 2, and 3 exactly. So these 1, 2, and 3 are your eigenvalues. So I'm calling it, let's say, lambda 1 for the first eigenvalue. This is 1, lambda 2. Sorry, lambda 2 is how much? Lambda 2 is 2, and lambda 3 is 3. These are the three roots. So these three are the eigenvalues of the matrix A. So basically, if I have to write it separately, eigenvalues are the roots of the characteristic polynomial. Okay, fine. Now what we do, another thing that we have to do is find the eigenvector as well. See, so these three eigenvalues will have eigenvectors corresponding to these eigenvalues. So we have to find three eigenvectors. So let's first start with the first eigenvalue and its corresponding eigenvector. So first, let's say lambda 1 equals to 1, this one, and its corresponding eigenvector, let me denote it by some v1. It's a vector, right? Do you know how to find eigenvector? I don't think you know because I think you told, right? You're not familiar with eigenvalues. Okay, so basically what we do is there is a eigenvalue equation, okay, which is of this form. The matrix here is A, right? A times the eigenvector, which is v1, is equal to its eigenvalue, which is lambda 1 times the same eigenvector. This is the eigenvalue equation, okay? So meaning that I mean, A acting on the vector, eigenvector, is same as some, you know, scalar multiple of the eigenvector itself. So the effect of this matrix acting on an eigenvector is simply, scaling of that vector by some constant uh, amount. And also one more thing, that eigenvector usually is non-zero. Okay, you don't take the all zero vector as an eigenvector. Eigenvector is non-zero. So this can also be rewritten as a minus lambda 1. Basically, if you change sides, lambda 1 times identity acting on v1 is equal to the zero vector. This is zero vector. Are you okay with this step? So basically I'm subtracting it. This will be a zero vector because I'm subtracting two vectors. Matrix acting on vector gives me a vector on the LHS. Some constant times vector is a vector. So both LHS and RHS are vectors. If I subtract them, I'll get a zero vector, which is this bold zero. Or this is the same thing as minus lambda I. Definitely I can write it also as identity acting on v1. Identity acting on v1 is also same as v1 itself. Now I can take common, is zero vector. Okay, all right. And in order to subtract something from A is a matrix. You also require a matrix. So that's how I introduced identity. So this is the eigenvalue equation. Okay, nice. So what is lambda 1? Lambda 1 is basically 1, right? So this reduces to A minus identity times v1 equals to the zero vector. So let me, so what is A minus identity? You already have the given matrix A, right? And you can simply subtract identity, and you can check that if you do that, where is the cursor? You'll get this matrix. And let me call this x1, x2, x3, okay? Some unknown It's a vector of unknown variables, the eigenvector v1. So eigenvector v1 is the eigenvector corresponding to the eigenvalue lambda 1. This is how we tell. Okay. So this is the all zero vector, which is 0, 0, 0. Clear? Is this clear so far? Hello? Okay. Yeah, you can just unmute and tell me. Otherwise, I might miss out on the chat box. Okay, so yeah, and now so what you have essentially is three set of linear equations in three unknowns. The unknowns are x1, x2, x3. If you find x1, x2, x3, you get v1, and v1 is what you want to find. That's the first eigenvector corresponding to the eigenvalue lambda 1. So you have to solve for this system of equations. So you can form these three equations and solve it. But usually, I mean, this has been discussed in the first week. I have discussed this in the first session. That what you do is, so this was your uh, A minus identity, right? This matrix. This is your zero vector. This is your V1. So you form an augmented matrix. You basically, in order to, because you'll have some system of three equations in three variables, you can simplify that further using Gaussian elimination or row operations, and you can convert this matrix into a particular form known as the row echelon form. Okay, I have discussed all that before. Okay. And in fact, professor has also discussed that in the first few weeks. So that actually simplifies your system of equations, but the solution remains the same. So that's the advantage. So what you do is take the augmented matrix. So the augmented matrix is basically this coefficient matrix, which is in our case A minus identity, this part, and you also concatenate it with the vector on the right hand side, which in our case is the zero vector, the vector on the right hand side. Okay, so you form a larger matrix like this. You take this and convert into REF, okay, which is known as row echelon form. Okay, so basically, what is the augmented matrix? This matrix, coefficient matrix on the left hand side, right? And I'm just using this line as a demarcation. There is not really any line. So you, and also you concatenate this zero vector on the right hand side with this. Okay, this is your augmented matrix. And what is the size of this augmented matrix now? Yeah, how many rows and how many
Oh,
columns?
3 cross 4?
3 cross 4, exactly.
Is it 3 cross 4?
Correct. Very good. So now you take this matrix and you convert into the row echelon form, and there are certain allowed row operations that you can perform, such as swapping or interchanging of two rows, multiplying a row by a scalar, non-zero scalar, adding a scalar multiple of one row to another row, like that. Okay, so and using those row operations, in this case I'm just mentioning the sequence of row operations that I performed. Okay, so R2 changes to R2 minus R1. I did this first. Then I did R3 changes to R3 plus 2R1. Then I did R3 changes to R3 plus R2. Okay, this sequence might be need not be unique. You can be, and by the way, the row echelon form is not unique. Okay, it depends on the sequence of steps that you perform. But there is something more called the reduced row echelon form or RREF, which is always unique. Okay, and if you do this sequence of steps, then what you will get is -1, -2, -3, 0, 2, 2, 0, 0, 0, and the right hand side always stays 0 actually, because in this case it's an all 0 vector, so doesn't matter whichever row operation you perform on this right hand side vector, it always stays all 0. Okay, so you see you have simplified this augmented matrix. You have introduced a entirely all 0 row in the third row, so that's the advantage. So now your system of equations will be simplified further, and these entries, do you know what these are called? These are called pivots. Okay, pivots are the first non-zero entry of a row in the row echelon form or the reduced row echelon form. So this is the row echelon form, and row echelon form has certain so -1 and 2 are the pivots. That is clearly visible, right? -1 is the first non-zero entry of the first row, 2 is the first non-zero entry of the second row, and there are no more pivots, correct? And in row echelon form, the condition is that if there is any all zero row, that has to be in the bottom of the matrix, which is satisfied here. There may not be a all zero row as well, but in this case there is, and if it is present, it has to be present at the bottom, which is satisfied here. And the pivot 2, the pivot 2 lies to the right of the pivot -1, which is in the row above it. So as you go downwards, the pivot should shift to the right of the previous pivot. Okay, that's the another criteria. So this is the row echelon form, and now from this row echelon form, and one more thing is that, okay, now can you tell me the system of equations from this row echelon form of the augmented matrix?
Minus x1 minus 2x2 minus 3x3.
Correct. So -x1 minus 2x2. And by the way, I mean, if you're completely familiar with these things, then I won't go into the details. Okay, let me know. Um, just for the
Okay,
sake of.
okay, okay. Yeah, you can skip that.
Oh, okay, okay, okay.
Okay.
Okay, 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 okay. Yeah, I was thinking like just in case if this is new, then that's why I was spending too much time. So now, so these are the two equations, right? And now so clearly there is a free variable. In this case, there is a free variable. So the pivot, there are two pivots, right? And in general, the rule is like whenever, um, I mean, this is a consistent system of equation. First of all, consistent meaning that it has a solution. There is a solution that exists. It could be a unique solution or it could be infinitely many solution, but it is consistent. There is at least one solution. So the way to check for consistency is that there should not be there should not be any pivot in the last column of the row echelon form of the augmented matrix. See, this is our last column, right? This is our last column. This is our last column. This does not have any pivot entry. So let's say if it had a pivot. Uh, so if this entry would have been non-zero, then the last equation would have been like 0 equals to some non-zero thing, which is absurd. So yeah, you have to check whether this last column of the REF of augmented matrix has any pivot or not. If it has a pivot, clearly you will say that it is an inconsistent system of equation, meaning that it has got no solution. Otherwise, if there is no pivot, then it is consistent. Now, consistent means there is some solution. It could be unique solution or infinitely many solution. So, and number of pivots is 2 here, and number of unknown variables is 3, x1, x2, x3. So number of pivots is less than the number of unknowns, and it is a consistent system. Since number of pivots is less than number of unknowns, you can conclude that there will be infinitely many solutions. Okay. For a consistent system, on the other hand, if the number of pivots is equal to the number of unknowns, if that would have been the case, then you could have said that the system has got unique solution. Okay, if number of pivots is equal to number of unknowns. But in this case, since number of pivots is less than number of unknowns, it has infinitely many solutions. And clearly, x3 is our free variable. How do you choose x3 as the free variable? Basically, you first observe the columns in which the pivots are located. So the pivots appear in the first and second columns. So first and second column. So they are also known as the pivot columns are also known as the basic columns. And the variables corresponding to those pivot columns are known as basic variables. So since the pivot columns are columns 1 and 2, your basic variables are x1 and x2. And the non-pivot column is the third column. So the third unknown variable, which is x3, is your free variable. Okay, so x3, sorry, x3 is your free variable, and x1, x2 are your basic variables, and the task is to express x1 and x2, the basic variables, in terms of the free variable. So if you, I mean, just solve these two equations, you will get x1 equals to minus 3. You are expressing x1 and x2 in terms of x3, which is your free variable. Okay. So now you have the eigenvector now. You have the eigenvector now. So the general solution, clearly there are infinitely many solutions. General solution is solution. We were finding v1. Remember that was this vector. So this is minus x3, minus x3, x3. So you can pull x3 out and you have minus 1, minus 1, 1. So x3 is your free variable. So you can choose it as per your wish. So I am choosing x3 equals to 1. So we get v1 equals to minus 1, minus 1 and 1. So this is your eigenvector corresponding to the eigenvalue lambda 1. And similarly, you can find the rest of the two eigenvectors as well. So lambda 2 equals to 2 and eigenvector v2. Okay. And similarly, I mean, if you just verify, I'm not writing the steps. You follow basically the same procedure. Okay. v2 equals to minus 1, 1, 0. Again, I mean, you'll end up with a free variable, and like previous time, I have again chosen the free variable to be 1. It depends on your choice. This eigenvector is not a unique, right? I mean, it depends on the
And
choice of the variable. Yeah.
okay, we can choose any of a free variable.
Sorry, your
Okay.
voice is breaking.
Uh, Free variable, any value we can choose, right? Where?
Except 0, because as I
Okay, okay,
said,
okay.
the rule is like you can't have a 0 eigenvector, but you can choose any other value. For example, if you refer to the lectures also, I think Professor Jagannatham, he chose a different value. I think he was getting something of the form of a fraction, so that's why, let's say 3 by 2 x, something like that. So that's why he chose x to be 2, to eliminate that fraction thing. So it depends on your choice. Yeah, if I get some eigenvector, you can come up with some scalar version of that as well, depending on your choice of the free variable. Okay, so yeah, so someone can also claim that he got -220. That's also makes sense. Okay, so now and similarly for lambda 3, verify v3 is v3 is -1 0. Okay, and just as a note, I'll mention that eigenvectors need not be unique. Okay, as we just said right now. Okay. mm, yeah, so I think this finishes this question. Now let's move to the fifth one. Okay, in fifth question we have to find the value of
Uh,
yeah, go ahead.
so this recording will be available, right, in the forum?
Yes, 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 yes. So
Okay, okay.
in the
Yeah,
course web
actually,
page,
my lab.
yeah, tell me.
No, no. Sorry, my laptop is going to be off. So thank you so much. So I'll anytime it will get
Oh,
off
okay, okay,
actually.
I get it. Okay, sure, no problem. This is all these things are recorded, and you can access them from the course web page, from the problem solving session tab. Okay, okay. So and for the fifth problem, you are given this matrix A, which is a 2 cross 2 matrix, and the entries are complex numbers. It's a complex matrix. You have to find the value of a scalar alpha such that alpha times A is unitary. So alpha times A has to be a unitary matrix. Okay. So this question is based on unitary matrix. So A is given as 1 minus iota, 1 plus iota, 1 plus iota, 1 minus iota. So this here, this iota is basically square root of. Okay. So it's a complex matrix, and alpha is a scalar that you have to find, and you're given that alpha times A is unitary. It's a unitary matrix. So what is the property of a unitary matrix? If alpha times A is unitary, then by definition of unitary matrix, alpha A times alpha A Hermitian is equal to identity. And also alpha in the other way also, other direction also, alpha A Hermitian times alpha A is also identity. So this is the condition for a unitary matrix. So what do you have? Alpha A. So if you split this Hermitian, the second term here, you will get A Hermitian times alpha Hermitian but it's same as alpha conjugate because alpha is a scalar and Hermitian means, so H denotes Hermitian, which is the transpose of the complex conjugate. Okay, and since alpha is a scalar, I mean it's not a vector, therefore transpose doesn't make any sense, so it's just the conjugate of that, and star here denotes complex conjugate. Okay, so this is yeah, this makes sense, and I have used the property that this is identity, since the property that I have used is, let's say if you have some p times q Hermitian, some product of two matrices p q, the whole Hermitian is equal to q Hermitian times p Hermitian. Okay, so now what do we have here? So this alpha and alpha star are, I mean, alpha and alpha star, these are some scalars. So you can club these two together. So alpha, alpha star, let me bring them ahead. And you have this thing is equal to identity. So what is alpha, alpha star? It's simply the magnitude square of alpha. And let's find this A Hermitian. Mm, this is a identity. So now let's find A Hermitian. So mod alpha squared. So A was this matrix 1 minus I, 1 plus I, 1 plus I, and 1 minus I. And its Hermitian would be, you have to take the transpose as well as the conjugate. So what you'll get is this. And this is identity, which means 1 0 0 1. Okay, and I mean you can multiply these two, I mean, matrices together. Simple matrix multiplication. I'm just writing the intermediate steps for completeness. This will be the first entry. This is the second entry. And this is hmm. So, and on the RHS you have 1001. Okay. Okay. Yeah, I'm not sure if I have made any mistake or not, but in plus or minus. So ultimately what you'll get is, this actually gets a nice form of a diagonal matrix, which is this. So clearly mod alpha squared is equals to 1 by 4, which tells you that alpha could be either plus minus half or plus minus half times iota. So it could be imaginary as well. These are the possible values of the scalar. That guarantees that alpha times A will be a unitary matrix. Okay. Okay. Yeah. Yeah. Okay. So for the last problem for today. So we have to find the vector. So we are looking at question number 6. We have to find the vector obtained by rotating the vector 1 minus 2 in the counterclockwise direction by 60 degrees. So clearly this is a problem based on the application of rotation matrix. Okay, this was also discussed. So you are given this vector 1 comma minus 2, right? This column vector 1 minus 2 in the 2D plane, and you are rotating. If you rotate this in the counterclockwise direction by an angle of 60 degrees, then what is the new vector that you get? That's the question. Okay, so okay, so basically, if you have to, think geometrically, let's say this is your xy plane, and the vector that you are given is the vector x1 is 1 minus 2. Okay, if you take this as your origin 0 comma 0, then let's say this is 1 unit, and okay, let me just extend this further. Okay, so and this could be 2 units. This is minus 2. So 1 comma minus 2, this point here. Okay, this is my given vector, original vector x1. Okay, mm, yeah, and I want to rotate this by an angle of 60 degrees in the counterclockwise direction. So if you rotate this, you'll get some vector like this. Okay, basically on rotating this by an angle of theta equals to 60 degrees in the counterclockwise direction. Okay, so if this resulting vector is x2, that is what you are asked to find. Okay, just a second. Okay, right. Now again, as I said, this is an application of the rotation matrix. So we are familiar with rotation matrix from the contents of week 3. So rotation matrix denoted by r of theta in the 2D plane. So this is the 2D rotation matrix. So in 2D, this is cos theta minus sine theta, cos theta. The effect of this rotation matrix r of theta is that it rotates a vector in the 2D plane by an angle of theta in the counter clockwise direction. Okay, so in our problem here theta is 60 degree, it is given. So what happens if we rotate the vector x1 in the anti-clockwise direction or the counterclockwise direction by an angle of 60 degrees. So the rotation matrix that we have in hand is r of theta, which is r of 60 degree, will be cos 60 degree minus sine 60 degree sine 60 degree and cos 60 degree. And this is nothing but cos 60 is half, sine 60 is root 3 by 2, okay. Now the now the new vector that you will obtain is by applying this rotation on your x1 vector. So this is equal to, the rotation is described by this matrix we just wrote, acting on x1. X1 is how much? 1 comma minus 2. This was our original vector before transformation, before rotation. Now it gets rotated to a new position defined by x2 bar, which is, if you perform this multiplication, you'll get half plus root 3 and minus half plus root 3 by 2. Okay, so this is the new resulting vector after rotation. So you see, and root 3 is I think something 1.7, something like that. So the x coordinate of this vector is half, which is zero point 0.5 plus some 1.7, so which is I think 2.2, around 2.2. And pictorially also it makes sense. You see, I mean, it had it has moved to the positive direction of the x-axis, right? So initially its x coordinate was 1. Now it has gone to some 2.2 or something, slightly more than that. And the y coordinate is minus 1 plus root 3 by 2. Root 3 by 2 is something, I think, how much? 1.7 by 2 is some 0.85, and minus 1, 0.85 minus 1 is something negative, right? Slightly negative. So which is, yeah, it's slightly negative, right? Okay, so this is your x2. And yeah, and I think with this we have come to the end of today's session. So I hope things were fine, and yeah, let me stop the recording, and we'll meet again on next Friday 6 p.m. Thank you.